Section 3, Complex Correlation. The learning objectives for this section are 1. Explain some reasons that researchers use complex correlational designs. 2. Create and interpret a correlation matrix. And 3. Describe how researchers can use partial correlation and multiple regression to statistically control for third variables. As we have already seen, researchers conduct correlational studies rather than experiments when they're interested in non-causal relationships or when they're interested in causal relationships, but the independent variable can't be manipulated for practical or ethical reasons. In this section, we look at some approaches to complex correlational research that involve measuring several variables and assessing the relationships among them. Assessing relationships among multiple variables. Most complex correlational research involves measuring several variables, either binary or continuous, and then assessing the statistical relationships among them. For example, researchers Nathan Radcliffe and William Klein studied a sample of middle-aged adults to see how their level of optimism, measured by using a short questionnaire called the Life Orientation Test, relates to several other variables related to having a heart attack. These included their health, their knowledge of heart attack risk factors, and their beliefs about their own risk of having a heart attack. They found that more optimistic participants were healthier. For example, they exercised more and had lower blood pressure. They knew more about heart attack risk factors and correctly believed their own risk to be lower than that of their peers. In another example, Ernest Jurilles and his colleagues measured adolescents' experiences of physical and psychological relationship aggression and their psychological distress. Because measures of physical aggression, such as the Conflict in Adolescent Dating Relationships Inventory and the Relationship Violence Interview, often tend to result in highly skewed distributions, the researchers transformed their measures of physical aggression into a dichotomous or binary measure, where 0 was did not occur and 1 was did occur. They did the same with their measures of psychological aggression and then measured the correlations among those variables, finding that adolescents who experienced physical aggression were moderately likely to also have experienced psychological aggression, and that experiencing psychological aggression was related to symptoms of psychological distress. This approach is often used to assess the validity of new psychological measures. For example, when John Cacioppo and Richard Petty created their need for cognition scale, a measure of the extent to which people like to think and value thinking, they used it to measure the need for cognition in a large sample of college students, along with 3 other variables: intelligence, socially desirable responding, which is the tendency to give what you think is the appropriate response, and dogmatism. The results of this study are summarized in Table 6.1, which is a correlation matrix showing the correlation, Pearson's R, between every possible pair of variables in the study. For example, the correlation between the need for cognition and intelligence was plus 0.39. The correlation between intelligence and socially desirable responding was plus 0.02, and so on. Only half of the matrix is filled because the other half would contain exactly the same information. Also, because the correlation between a variable and itself is always 1, these values are replaced with dashes throughout the matrix. In this case, the overall pattern of correlations was consistent with researchers' ideas about how scores on the need for cognition should relate to the other constructs. Factor analysis. When researchers study relationships among a large number of conceptually similar variables, they often use a complex statistical technique called factor analysis. In essence, factor analysis organizes the variables into a smaller number of clusters, such that they're strongly correlated within each cluster, but weakly correlated between the clusters. Each cluster is then interpreted as multiple measures of the same underlying construct. These underlying constructs are also called factors. For example, when people perform a wide variety of mental tasks, factor analysis typically organizes them into 2 main factors: one that researchers interpret as mathematical intelligence, like arithmetic, quantitative estimation, spatial reasoning, and so on, and another cluster that they interpret as verbal intelligence, things like grammar, reading comprehension, vocabulary, and so on. The big five personality factors have been identified through factor analysis of people's scores on a large number of more specific traits. For example, measures of warmth, gregariousness, activity level, and positive emotions tend to be highly correlated with each other and are interpreted as representing the construct of extroversion. As a final example, researchers Peter Renfro and Samuel Gosling asked more than 1,700 university students to rate how much they liked 14 different popular genres of music. They then submitted these 14 variables to a factor analysis, which identified four distinct factors. The researchers called them reflective and complex, which was things like blues, jazz, classical, and folk, intense and rebellious, rock, alternative, and heavy metal, upbeat and conventional, which was country, soundtrack, religious, and pop, and energetic and rhythmic, things like rap, hip hop, soul, funk, and electronica. You can see this in Table 6.2. Two additional points about factor analysis are worth making here. One is that factors are not categories. Factor analysis does not tell us that people are either extroverted or conscientious, or that they like either reflective and complex music or intense and rebellious music. Instead, factors are constructs that operate independently of each other. So people who are high in extroversion might be high or low in conscientiousness. And people who like reflective and complex music might or might not also like intense and rebellious music. The second point is that factor analysis reveals only the underlying structure of the variables. It's up to the researchers to interpret and label the factors and to explain the origin of that particular factor structure. For example, one reason that extroversion and the other big five operate as separate factors is that they appear to be controlled by different genes. Exploring causal relationships. Another important use of complex correlational research is to explore possible causal relationships among variables. This might seem surprising given the oft quoted saying that correlation does not imply causation. It is true that correlational research cannot unambiguously establish that one variable causes another. Complex correlational research, however, can often be used to rule out other plausible interpretations. The primary way of doing this is through the statistical control of potential third variables. Instead of controlling these variables through random assignment or by holding them constant as in an experiment, the researcher instead measures them and includes them in the statistical analysis called partial correlation. Using this technique, researchers can examine the relationship between two variables while statistically controlling for one or more potential third variables. For example, assume a researcher was interested in the relationship between watching violent television shows and aggressive behavior, but she was concerned that socioeconomic status, SES, might represent a third variable that's driving the relationship. In this case, she could conduct a study in which she measures the amount of violent television that participants watch in their everyday life, the number of acts of aggression that they have engaged in, and their SES. She could first examine the correlation between violent television viewing and aggression. Let's say she found a correlation of plus 0.35, which would be considered a moderate size positive correlation. Next, she could use partial correlation to re examine this relationship after statistically controlling for SES. This technique would allow her to examine the relationship between the part of violent television viewing that is independent of socioeconomic status and the part of aggressive behavior that's independent of socioeconomic status. If she found that the partial correlation between violent television viewing and aggression while controlling for SES was plus 0.34, that would suggest that the relationship between violent television viewing and aggression is largely independent of SES. That is, SES is not a third variable driving that relationship. On the other hand, if she found that after statistically controlling for SES, the correlation between violent television viewing and aggression dropped to just plus 0.03, then that would suggest that SES is indeed a third variable that's driving that relationship. If, however, she found that statistically controlling for SES reduced the magnitude of the correlation from plus 0.35 to plus 0.20, then this would suggest that SES accounts for some, but not all, of the relationship between television violence and aggression. It's important to note that while partial correlation provides an important tool for researchers to statistically control for third variables, researchers using this technique are still limited in their ability to arrive at a causal conclusion because this technique does not take care of the directionality problem, and there may be other third variables driving the relationship that the researcher didn't consider or statistically control. Regression. Once a relationship between two variables has been established, researchers can use that information to make predictions about the value of one variable given the value of another variable. For instance, once we've established that there's a correlation between IQ and GPA, we can use people's IQ scores to predict their GPA. Thus, while correlation coefficients can be used to describe the strength and direction of relationships between variables, regression is a statistical technique that allows researchers to predict one variable given another. Regression can also be used to describe more complex relationships between more than just two variables. Typically, the variable that's used to make the prediction is referred to as the predictor variable, and the variable that's being predicted is called the outcome variable or criterion variable. The regression equation has the following general form: y equals b sub 1 x sub 1. Y in the formula represents the person's predicted score on the outcome variable. B sub 1 represents the slope of the line depicting the relationship between the two variables, and x sub 1 represents the person's score on the predictor variable. You can see that to predict a person's score on the outcome variable y, one simply needs to multiply their score on the predictor variable x by the regression weight b sub 1. When simple regression involves using one variable to predict another, multiple regression involves measuring several variables, x1, x2, x3, and so on, and using those to predict some outcome variable y. So in other words, there are multiple predictors being used in this one equation to predict the outcome variable. Multiple regression can also be used to simply describe the relationship between a single outcome variable, y, and the whole set of predictor variables, x1, x2, x3, and so on. The result of a multiple regression analysis is an equation that expresses the outcome variable as an additive combination of the predictor variables. So the regression equation has the general following form: y equals b sub 1 x sub 1 plus b sub 2 x sub 2 plus b sub 3 x sub 3, and so on. The regression weights, the b sub 1, b sub 2, those indicate how large a contribution each individual predictor variable is making on average to the prediction of the outcome variable. So imagine each of those predictors is contributing part of the outcome variable, or how you would predict that outcome variable, and the b sub 1, b sub 2, that represents how much of an impact each of those has. Specifically, they indicate how much the outcome variable changes for each 1 unit change in that predictor variable. The advantage of multiple regression is that it can show whether a predictor variable makes a contribution to an outcome variable over and above the contributions made by the other predictor variables. So it can be used to show whether a predictor variable is related to an outcome variable after statistically controlling for the other predictor variables. As a hypothetical example, Imagine that a researcher wants to know how income and health relate to happiness. This is tricky because income and health are themselves related to each other. Thus, if people with greater incomes tend to be happier, then perhaps it's only because they tend to be healthier. Likewise, if people who are healthier tend to be happier, perhaps it's because they tend to make more money. But a multiple regression analysis, including both income and health as predictor variables, would show whether each one makes a contribution to the prediction of happiness when the other is taken into account or when it's statistically controlled for. In other words, multiple regression would allow the researcher to examine whether that part of income that is unrelated to health predicts or relates to happiness, as well as whether that part of health that's unrelated to income predicts or relates to happiness. Research like this, by the way, has shown both income and health make extremely small contributions to happiness, except in cases of severe poverty or illness. The examples discussed in this section really only scratch the surface of how researchers use complex correlational research to explore possible causal relationships among variables. It is important to keep in mind, however, that purely correlational approaches cannot unambiguously establish that one variable causes another. The best they can do is show patterns of relationships that are consistent with some causal interpretations and inconsistent with others.